We continue on review on concepts from basic chemistry, and in this video we're also going to add in a couple of ideas that we really didn't cover in basic chemistry. We'll kind of hit some real fundamental concepts that are necessary, and then we'll amplify them in our later study when we get into organic chemistry. So our first thing we need to review is atomic spectra. And we talked a little bit about this, the fact that energy levels in atoms are quantized. So what does that mean? Well, let's take an atom like carbon. Carbon has 6 electrons. Those electrons, it turns out, go into specific energy states. So each atom has only a certain number of energy states that exist, and electrons must plug into those energy states. In fact, those energy states and how they behave, they really control all of chemistry. So if you remember, we had 3 quantum numbers that define each energy state, or each what we call atomic orbital. And those 3 values are shown on the left-hand side here. The n value, that is the principal quantum number, the L value, that is the angular momentum, and the m sub L value, which is sometimes called the magnetic quantum number or the orientation. So it turns out that the n value is the primary determinant of the size of the atomic orbital, that is how far the electron is from the atom, and that is the primary determiner of the energy of the orbital, or that energy level. The angular momentum value, the L value, is typically associated with the shape. And there are 3 that we'll focus on mostly in this course. That is L values of 0, 1, and 2. We're really going to focus on 2, primarily the L value of 0 and the L value of 1. And then the m sub L value just tells which direction that particular orbital or energy state is pointing. So if you have an L value of 0, like shown here, we call that an s orbital. So you can have an s orbital in the n equals 1 state, or 2 state, or 3 state, or any state for that matter. They'll have an s orbital. And then if you are in the n is 2 or 3 or higher state, you can have a p orbital. That would be an L value of 1. Now we'll find out that the d orbitals really only occur in quantum numbers, principal quantum numbers 3 and higher. And you'll notice here that for each s orbital, or each s state, there's only one m sub L value, that is 0. So if n is 1 and L is 0, m sub L is 0. If n is 2 and L is 0, then m sub L is 0. And if n is 3, L is 0, and m sub L is 0. If you have, on the other hand, a value of 1 for the L value, then you have a p-type orbital, or p energy state. Then the m sub value can be -1, 0, or +1, and those all turn out to be equal in energy, but they just point in the 3 directions, x, y, and z axes. So there's no p-value for n is equal to 1, but for n is equal to 2, if you have an L of 1, that is a p orbital, then the m sub L can be -1, 0, or +1. If n is 3, then you can still have a L value of 1, and again, likewise, your m sub L value can be -1, 0, or +1. Now, if we're in the 3 state, the n is equal to 3 state, then our L value can be 2, and if L is 2, then m sub L can be -2, -1, 0, +1, or +2. Now, it turns out for each one of these states listed on here, you can put 2 electrons into that particular state, but only 2. So you can never put more than 2. So there's no case where we ever observe an orbital that has more than 2 electrons in it. So now each of these orbitals or energy states has a kind of a geometrical shape. So in the upper left-hand corner here, you have the 1s, the 2s, and the 3s orbitals, and that's shown in the center. They tend to be, they've done a cross-section here. They tend to be spheres. They're circular, okay? The p states tend to be shaped like dumbbells, and that's shown over on the upper right-hand corner, and you can see they're shown in kind of a brownish color. The d orbitals, they can have a variety of shapes. There's 5 different ones, and we won't worry about those so much. So in terms of the energies, if we're just looking at a hydrogen atom, I don't know if you recall this, but the energies of the hydrogen atom, the orbitals follow this diagram here. So the 1s orbital is the lowest energy. That's what we call the lowest energy state. And there's 2 electrons that can go into that state. Now the n is equal to 2 state, for hydrogen, the 2s and the 2p are all at the same energy level, though we'll see later on that the p's can sometimes be a little higher for other atoms. And of course, each of those can have 2 electrons as well. So you can see the 2s could hold 2 electrons, and the 2p can hold a total of 6 electrons, because there are 3 orbitals. Remember, that's for the L is equal to 1, so m sub L can be minus 1, 0, or plus 1. And there can be 2 electrons in each of those orbitals. So now this kind of gives us some insight into why the periodic table has the structure that it does. Now the reason the periodic table is arranged this way is because of we're looking at elements with similar properties. That's the reason for this. But it turns out that there's an underlying principle that helps us to understand why it is structured as such. Now, these are all the elements, but of course, for this course, it turns out the elements that we're going to focus on primarily are in the red box, plus hydrogen. So a hydrogen atom plus boron, carbon, nitrogen, oxygen, and fluorine. We really won't worry about neon because that doesn't chemically bond. That's an inert gas. And we'll focus primarily on the ones in orange, that is carbon, nitrogen, oxygen, and fluorine. Now it turns out that the filling of electrons into the energy states is why we have this structure here. And we have 4 different regions, what we call the S block, the P block, the D block, and the F block. So now the S block means that the last electrons are going into S-type orbitals. And so there's only one S orbital for each value of n. So in this case, the n value would be listed as being associated with the period. So notice on the left-hand side of the periodic table it says period. And it goes from the top down to the bottom, 1, 2, 3, 4, 5, 6, 7. The period designates the n value for the last electrons that are going into the system. So, for example, with hydrogen, 1 electron is going into an s orbital. So that's the n value of 1. So the s block, you can see there's only 2 elements that are in the s block because the s orbital can only take 2 electrons, and so everybody in group 1 and group 2 is filling up either 1 or 2 electrons into that last s orbital. On the left-hand side, we see the p block, and we'll spend a lot of time with the p block this semester. The p block is filling, as you would guess, the p orbitals. And there are, since L is equal to 1 for the p value, the m sub L is minus 1, 0, and plus 1, there are 3 different orbitals, and each orbital can take 2 electrons. So there are 6 electrons going in to the last p orbitals, the highest energy p orbitals, for the elements in the p block. Now, the D block and the F block, we really won't spend a lot of time with those, but let's just mention those right now since we're on to this. The D block has 5 orbitals because we're dealing with the L is equal to 2 value, so m sub L can be -2, -1, 0, +1, and +2. That is, there's 5 different orbitals. Each of those orbitals can house 2 electrons. So there's 10 different elements that can be filling. So if you look at that D block, and let's look at the first row, you can see SC, that is scandium, has 1 electron going into the D block. And by the time we get to the end, all the way on the right-hand side, that's Zn, that's zinc. Zinc has 10 electrons filling up that D block. And finally at the bottom is the F block. We won't spend any time on the F block, but since we're here, you'll notice that it's 14 across. It's 14 across because L is equal to 3. L is equal to 3 is the F orbitals. And so m sub L can be -3, -2, -1, 0, +1, +2, and +3. That is, there are 7 different orbitals, each holding 2 electrons. That gives us 14. So there are 14 elements across there. So let's just look at the red box one more time. We're going from boron across to neon. We're filling the 2p subshell. So we have a 2p1 for boron, 2p2 for carbon, 2p3 for nitrogen, 2p4 for oxygen, 2p5 for fluorine, and 2p6 for neon. Next up, we're going to talk about valence electrons, and we'll go into detail more about this later on, what the definition of valence electrons are, but I just want to tie it back to our periodic table. For the n is equal to 2 value, if for n is equal to 2, so that is the second period, that is the second row on the periodic table, you'll notice there are 8 spots there. So that means that there's 2s and there's 3 2p's. So lithium has 1 valence electron going into the 2s. Beryllium has 2 electrons going into the 2s. Boron, which is element 5, has 2 electrons in the 2s and 1 in the 2p. That's 3 electrons. So these are 3 highest energy electrons. Carbon has 4. 4 of its 6 electrons are these high energy ones. So we've got 2 2s's and 2 2p's. Nitrogen has 5 valence electrons because there are 2 in the 2s, 3 in the 2p. Oxygen has 6 valence electrons, that is 2 in the 2s and 4 in the 2p. Fluorine has 7. So there are 2 in the 2s and 5 in the 2p. So now we'll continue on thinking about valence electrons and what those mean. So valence electrons, by definition, these are the electrons in the highest energy levels or orbitals in the atom. Now there's actually more subtlety to this, and we're not going to have time to cover it. So this is not an exact definition, because it turns out when you get to the D block and the F block, you can be filling lower values of N, but for our purposes, for the P block, for organic chemistry, we're filling in the highest energy levels in the atom. Secondly, the electrons in an atom which are involved in chemical bonding are the valence electrons. They're the ones that do all of the chemical interactions. They cause the chemistry. They're lost and gained by atoms. For the period 2 atoms, the ones most important for organic chemistry, all the atoms in the n is equal to 2 level are valence electrons. So let's complete a table. So here's a table. You've got an element N, O, F, C, and H. That is nitrogen, oxygen, fluorine, carbon, and hydrogen. So I want you to write down the total number of electrons in the atom. You would know that from your last video. And then from this video, let's determine the number of electrons in each of these atoms. So stop the video and complete this table. And when you're done, come on back. Okay, so now we're back. And let's kind of fill this in. For nitrogen, I've already shown you the answer. There are 7 total electrons because this is the 7 is the atomic number for nitrogen. 5 of those electrons are valence electrons, 2 of the 2s and 3 of the 2p. For oxygen, there are 8 total electrons and 6 are valence electrons. So there are 6 involved in chemical bonding. Fluorine has 9 total electrons, 7 that are valence. Carbon has 6 electrons, 4 of them are valence. And then hydrogen has 1 electron, and it is a valence electron. Now we're going to talk about what's called the octet rule, and we'll cover this on a couple of different slides. But the basic idea here is, for a main group, that is the p block elements, like we see in organic chemistry, they tend to bond such that each atom ends up with 8 electrons in its valence shell. You say, where do they come from? Those are the unpaired electrons plus the bonding electrons, and those can be shared by other atoms. And those 8 electrons then give it the same electron configuration as the nearest noble gas. So electronically it looks like a stable system, a noble gas. So for example, carbon has 4 valence electrons. We know that from the last slide. There's 6 total, 4 of them are valence, the 2 2s and the 2 2p's. It turns out it tends to form 4 covalent bonds with other atoms. So its 4 electrons plus the 4 electrons that are shared by other atoms gives it a total of 8 shared electrons. We call that an octet. Now next, we can look at a nitrogen atom. A nitrogen atom has 5 valence electrons, 2 2s and 3 2p's. These tend to form 3 covalent bonds with other atoms, so that the 5 valence electrons from nitrogen, typically, and we'll see later on, we'll call that a lone pair and 3 bonding pairs, plus the 3 electrons that come from other atoms through their bonds give a total of 8 for the nitrogen atom. So it looks like it has an octet. Now, when we form a covalent bond, typically a molecule will gain, lose, or share electrons to achieve that noble gas electron configuration. Now for ionic compounds, we talked about this in basic chemistry. So for example, sodium chloride, sodium would lose 1 electron because everybody in group 1 would lose 1 electron to achieve the nearest noble gas configuration. And then the chlorine would pick that electron up and form chloride. That's why we would call it sodium chloride. But in molecular compounds, we don't gain and lose electrons. We share electrons in order to achieve the nearest noble gas configuration. So let's take the simplest case that we can look at. That is hydrogen gas, H2. Why does H2 exist as H2 and not as H3 or H4? Well, let's consider this. Each hydrogen atom has 1 electron. Now the nearest noble gas is helium, and that has 2 electrons. And so 2 hydrogen atoms will come together. Each will share 1 electron, so that each electron can claim that it is sharing 2 electrons. Those 2 electrons then give each one the same electron configuration as the nearest noble gas, that is helium. So if you go back and look at your periodic table, you have hydrogen and helium. So now this leads us to what we call the octet rule and the duet rule. So the p block elements, particularly the period 2 p block elements, carbon to fluorine, tend to follow the octet rule. In fact, they follow this pretty rigorously. It turns out that for those elements, carbon to fluorine, the atoms gain, lose, or share electrons to achieve a stable noble gas configuration And in this case, that would be a 2s2, 2p6, such that it would have 8 valence electrons. Hydrogen, of course, is only in period 1. It's the one element that's by itself there, and it tends to follow the duet rule. That is, it wants to have 2 electrons to be like helium. So here's kind of a quick summary of the carbon through fluorine sort of bonding characteristics. So let's look at each one. So the element and we're just going to focus on the first row of this table and the third, fourth, and fifth rows, and then we'll think about that other row in a second. So for the elements in period 2, we have carbon, nitrogen, oxygen, and fluorine. For each of these, a dot has been drawn to represent each of the valence electrons. Carbon has 4 valence electrons, the 2 2s's and 2 2p's. Nitrogen has 5, oxygen has 6, fluorine has 7. So carbon has 4 valence electrons. Nitrogen has 5 valence electrons. Oxygen has 6 valence electrons. And fluorine has 7 valence electrons. Now, for carbon to achieve an octet, it would have to add 4 more electrons, so it will need 4 more bonds. Nitrogen needs 3 more electrons to get to an octet, so it will tend to form 3 bonds. Oxygen will need 2 electrons to form the octet, so it will form 2 bonds. And likewise, fluorine needs 1 electron, so it will form 1 bond to create its octet. Now, it turns out for many organic compounds, period 3 can be involved. So there are organosilicon compounds, organophosphorus compounds, and then sulfur and chlorine as well. And they tend to follow this pattern, but they'll show a lot more deviations. And so we won't focus too much on those elements. They'll turn out to be important later on in biological chemistry, and we'll discuss them in detail then. So what we're going to do next, and this is the last thing we're going to cover in our video, is what we call Lewis structures. So just like we do dots for the electrons around an atom, we can draw lines to show chemical bonds forming. And this is something called a Lewis structure. They were developed by G.N. Lewis, probably one of the greatest American chemists ever, brilliant chemist. And G.N. Lewis developed Lewis structures. Think of them as a cartoon representation of a molecule. We can't see molecules. We can infer their existence, and we can see electronic signals from them, but we can't actually see them with the eye. They're too small. They're much smaller than the wavelength of light, and so we don't ever see them as such. But we can draw pictures that give us an idea of what they look like. They'll help us to understand what is their shape. And this will be very important for organic chemistry. Lewis structures are massively important for organic chemistry. So a Lewis structure is a diagram of a molecule or a polyatomic ion or some chemical system, and it shows the shared pairs of electrons or the shared electrons in bonds as straight lines, and then the unshared electrons are lone pairs. So here's an example. Here's a molecule, hydrogen chloride, HCl. So on the last slide we saw that chlorine had 7 electrons. 1 was shared. And so we need to pick up an extra electron to give chlorine an octet, and hydrogen needs 1 electron to make a duet. So what we do is we draw a line, 1 electron from chlorine and 1 from hydrogen. So each line represents 2 electrons, 1 donated by each atom. So hydrogen chloride then has 1 line between it, showing the molecule hydrogen chloride. Now, what are the other electrons from chlorine? Because remember, chlorine has 7 valence electrons. Well, it turns out that they'll all sit in kind of p-type orbitals. They're actually really strictly sp3 orbitals, but those 3 electrons are all paired up in 3 orbitals. So here, hydrogen in HCl has 1 valence electron. It's shared in 1 covalent bond, represented by the solid line. Chlorine has 7 valence electrons. Only 1 of them is shared. The other 6 are unshared electrons. They're lone pairs, and they're represented by pairs or pairs of dots or the lone pairs. And lone pairs actually do manifest themselves. We can see their physical and chemical behaviors manifest, so those are a real thing. So next up we have multiple bonds. That is, what we call single bonds, double bonds, and triple bonds. And these will be very important as we move on through alkenes, alkynes, and aromatic compounds, and other sorts of organic structures. So it turns out, hydrogen chloride shown here has 1 line between the hydrogen and the chlorine because it's sharing 2 electrons, 1 from chlorine, 1 from hydrogen. But sometimes atoms can share more electrons. So for example, in molecular oxygen, O2, each atom shares 2 electrons, so that there are 4 total electrons being shared. Those 4 electrons form what we call 2 bonds or a double bond. Now, you can also have up to 6 electrons shared. So, for example, in nitrogen, molecular nitrogen, N2, the nitrogen gas that makes up most of the atmosphere, each nitrogen atom shares 3 electrons. Because remember, nitrogen has 5 valence electrons. It turns out 2 are in lone pairs. Nitrogen tends to form 3 bonds. So for N2, there are 3 bonds. Each one is sharing 3 electrons. There's 6 total shared electrons. That is a triple bond. It turns out that we're not going to cover these. The highest bond order you can have is a quadruple bond. If you're really interested in the future, maybe you can study more chemistry and learn about those. But our highest bond order for organic chemistry is going to be a triple bond. So let's look at some Lewis dot structures for different molecules. So the first one we're going to put up is the first organic molecule we'll look at when we get to organic chemistry. That is methane gas. Its chemical formula is CH4. And we know that the carbon atom sits in the center, and there are 4 hydrogen atoms around it. Carbon has 4 electrons. Each one can form a bond. So carbon forms 4 bonds. Each hydrogen can form 1 bond. So each carbon-hydrogen interaction is a single bond. There are 4 single bonds around carbon. Next up, let's look at water. Water involves oxygen and 2 hydrogens. The oxygen has 6 valence electrons. It needs 2 more to form its octet, so it will form 2 bonds. So 4 of its electrons are in lone pairs, the 2 on the top left and the 2 on the top right. And then the remaining 2 electrons are in bonds. So 1 hydrogen atom will bring 1 electron, and the oxygen will share an electron to create a bond. And then a second hydrogen will take that second electron that oxygen has to bond and form a second bond. And then finally we have ammonia, NH3. Nitrogen has 5 valence electrons. It tends to form 3 bonds. So 3 hydrogens, each one will bring in an electron and share with one of the nitrogen electrons to form 3 single bonds. And then the other 2 electrons from nitrogen sit in a lone pair. Next up, let's look at hydrogen fluoride. Very similar to hydrogen chloride, fluorine is the first halogen in group 17. It has 7 valence electrons. It needs 1 electron to form its octet, so with HF, hydrogen brings in 1 electron, fluorine brings in 1 electron, they form a single bond. The other 6 electrons that are valence electrons for fluorine go into 3 lone pairs. Finally, we can look at carbon tetrafluoride. We'll look at this molecule later. This is a more complex structure. Carbon has 4 valence electrons. It needs 4 bonds to complete its octet, so carbon forms 4 bonds. Each fluorine atom has 7 valence electrons and needs 1 electron to complete its octet, so fluorine will form a single bond. Therefore, each fluorine will bond to carbon 1 time. So there are 4 single bonds, 4 single carbon-fluorine bonds to form carbon tetrafluoride. And we'll look later on at what this implies about what the topology or molecular shape of the system is. We'll use those molecular model kits to help us to understand that later. That's the end of our review. There'll be a review assignment for you to work on as well. And then you can dive into the main organic chemistry.